All right. So I'm going to start this off by addressing the question, well, what can you study using drift diffusion modeling? And I'm going to introduce this using Cream. Some of you might remember listening to the song. It's by the Wu-Tang Clan. It's released in 1993. Absolute stone cold hip hop classic. If you haven't listened to it after the session's over, go to YouTube and listen to it. Very good song, holds up over the years. I bring this up because we're going to actually be repurposing this acronym to talk about drift diffusion modeling, right? So CREAM can also, in this case, stand for choices and reaction times enable an accurate speed trade-off. And we're going to see how we can use the drift diffusion model to do this, okay? And so the roadmap that we're going to be taking to talk about all of the material in today's workshop, right? So just to give you an overview of how DVM has been used in the past in regards to choices, traditionally it's been used to try and explain what I'm calling low-level cognition. What I mean by low level is things that are a little bit more perceptual. So random dot motion tasks, for example, inhibitory tasks like the stop signal task, or tasks that require, attending to response conflict. So you're probably familiar with the Stroop tasks, the flanker tasks. And so when you need to exert cognitive control, the drift diffusion model can give you an explanatory set of mechanisms as to how people are responding in these tasks. But there have been some really exciting recent extensions to this work. For example, in the realm of value-based decision-making. So for example, some of the work by Amitai Shenhav has looked at the interplay between reward and attention in decision-making tasks using DVM. There's some really exciting work looking at people's personal preferences for different kinds of foods or different kinds of options that are entirely value-based. And even more recently, and this is where my sort of personal expertise is in, and talking through social and moral preferences. So Sandra Hutcherson has this really nice paper on how people make altruistic choices, uses the DVM to characterize how people do this. Also has a line of work on food preferences for when you're choosing for yourself versus for when you're choosing for another person who maybe has a healthier lifestyle than you do. And so even though you might not choose broccoli for yourself over, I don't know, a pack of Cheetos, you recognize that for somebody else, broccoli might be more valuable. And then the work that I'll talk about at the very end of today's session is talking about conformity to other people's moral values or to a group's moral values. And we use drift diffusion modeling to characterize how people conform to a group, right? So there are some limitations to using DVM. It's a good model for a particular subset of choices that satisfy these criteria. So the first and most important thing is that all of the choices that you can model using DVM must be binary choices, right? And so in a random dot motion test, for example, you'd be looking at whether the dots are moving left or right. In a value-based decision-making task, you could maybe characterize whether somebody says yes or no to something. Or in some other test, you might say you responded correctly or you responded incorrectly. These decisions have to be relatively fast. This review by Ratcliffe and McCune suggests that the mean reaction times in your binary choice task should be less than 1,000 to 1,500 milliseconds. In practice, actually, we've used DVM to model choices that are quite a bit slower than this. And we found that this works well in some cases. So like in the conformity experiment that I'll show you later. And it works somewhat less well in other cases when people deliberate for too long or have a fixed or rigid stimulus response kind of mapping. So one line of work that we've recently had some difficulties with is actually a charity donation task. And some people are just so generous that they say, I want to donate on every trial. They don't deliberate. It's not a drift diffusion process. There's no variability in their choices, and we see very fast reaction times. So in that case, actually, this is a problem with uncertainty, right? when you know exactly how you want to respond in every trial, there's actually no uncertainty, nothing for you to consider. And so the DVM actually might not be a very good process model of those kinds of choices. Right, so this just gives you an overview of some of the criteria that describe assumptions about the decision process that people are using to make choices. And we're going to talk about that in much more detail a few slides from now. Right. So the second piece of DVM modeling is, of course, reaction times. So what I did here is actually just did a Google image search for reaction time distribution, and I picked out a whole bunch of figures from what look like cognitive science papers at random, pulled from a variety of tasks, domains, experimental questions. And you'll note that basically you see the exact same pattern across all of these, right? All of these distributions are right skewed, meaning relative to a normal distribution, it has a long tail to the right. And this is basically a sort of canonical shape that you should expect to see in reaction time experiments that satisfy the criteria that I mentioned earlier, right? In binary choice decisions, where there's some amount of uncertainty that you have to resolve. As you would expect, the easier the decision is, the faster you are to make choices. So another thing that you might notice is that some of these reaction times are shifted in time. So shifted, basically you take the whole distribution and move it, nudge it to the left or right, depending on maybe the choice difficulty. You might also notice that some of these reaction times distributions are broader or narrower, right? Depending on the amount of uncertainty that's evoked by the decision. But ultimately, the big takeaway here is that this is the canonical shape that shows up time and time again when you measure reaction times in two choice decision tasks. Okay, so that's all good and fine, but you might ask, well, why do we need a model, right? So we know from the study of economics, decision sciences, that of course, examining what choices people make is obviously very illuminating about what might be going on in people's minds. We also know from cognitive science and neuroscience that reaction times matter. And so you might ask, well, why can't we just look at the raw data, right? Why can't we just take a look at the choices that people are making and then separately, maybe log transform your reaction times and do a linear regression on that? In other words, what do we gain from modeling these things together jointly in the same model? And this is where we get to the speed accuracy trade-off. All right, so remember back to when you were a teenager, right? And now imagine that you're talking to your crush, whoever that might have been. You're having a great conversation. And so you decide, well, maybe I'll ask them on a date. So there are essentially four possibilities for what might happen. You might ask your crush on a date and they say yes. You might ask and then they say yes. They might say no, or they might say no thanks, right? Well, note, each of these responses actually gives us different information about what might be going on in the mind of your perhaps unrequited love. So knowing the choice obviously is important because you want a particular outcome. You want to go on a date with somebody that you like, but so is knowing how difficult or how uncertain the choice was, right? And you can infer that using reaction time as a proxy. The longer it takes for somebody to respond, the more you suspect maybe they're just being nice. Maybe they don't actually want to go on this date with me. All right, and so this brings us to the speed accuracy trade-off. I'm going to now illustrate that in terms of like cognitive tasks, right? And the easiest task that we can use to understand it is the random dot motion task. So we've got the schematic here. So just in case you're not familiar, some proportion of these dots are moving in one direction while other dots are moving basically at random. And the task that participants are required to do is judge what direction dots are moving. So when you see that motion coherence is 50%, right? So 50% of dots are moving in one direction. You can imagine that this is a fairly difficult task. You can optimize for being accurate by carefully observing the stimulus over a long period of time. And what that would do is produce high accuracy, but at the cost of slower reaction times, right? You could alternatively optimize for speed, right? By making a fast judgment that's not very accurate. So this produces fast reaction times, which is great if you're perhaps a bad participant and you're bored with the task and you just want to get through the remaining trials really quickly. But you would expect that such a person would have fairly low accuracy. Of course, in practice, we're trying to always strike some balance between speed and accuracy. Unless the decision is trivially easy, like when motion coherence is 100%, we can't have both speed and accuracy. There is some uncertainty in the world that we must resolve. And so the DBM is all about how you look at evidence from the world to be able to resolve that uncertainty and make decisions, right? And most of the decisions that we're interested in as researchers are, in fact, not trivial, hopefully. They're ones in which the decision is uncertain and therefore more difficult. And I should say, just as a sort of side note, the DBM was first used to examine lower level cognitive processes where there's an objectively correct answer, right? As in the dot motion task. And responses can be coded as being correct or incorrect. And that's why this trade-off is labeled as one versus speed versus like accuracy, quote unquote. But I do want to note that this trade-off also applies to other kinds of value-based decision-making scenarios. So in this paper, participants are asked to make social decisions in which they're choosing between selfish and altruistic choices. And there's not really an accurate answer, right? Everyone has different moral beliefs about the value of behaving altruistically. But the argument that they make in this paper is that a selfish person can sometimes make altruistic choices by accident, basically. And so responding faster has actually led them to make a mistake. And so you can see that the speed to accuracy trade-off can look differently depending on the sort of decisions that you are studying in the domain that you're studying those decisions in. All right, so that gives you, sort of a high-level idea of what you can study using DBM. And now we're going to jump to understanding how DBM works. Right? So this is just a big picture overview of everything. We're going to walk through all of these main 4 parameters here in quite a lot of detail. And by the time that we're done, hopefully, you should be able to understand what's going on in this figure here, which may look very busy to you, but all will be revealed in a few slides. Afterwards, I will briefly touch on some extensions to the DBM that you might find interesting, time permitting. We'll see. All right, so decisions, of course, unfold over time. So that's the first thing that we've got to plot out. And at each time step, it's assumed that you noisily accumulate evidence in favor of one choice over another. And that's represented by these boundaries here, right? And so this is where the name drift diffusion comes from. It's as if you are drifting towards a choice. So when do you execute an action? So because the model contains these decision boundaries, the idea is once you've accumulated enough evidence over time to cross over one of these boundaries, that's when the choice is made. Depending on how difficult or uncertain the decision is, you'll accumulate evidence at different rates on average. And we'll call that the drift rate. And we call it the drift rate because it's the rate at which you are drifting towards one decision boundary or another, right? And so that's represented here by this arrow. In practice, of course, there's going to be some noise around this arrow as you drift towards one decision or another until you hit a decision boundary. So let's consider, just as a concrete example, an example of the random dot motion task with 50% motion coherence. So there's a moderately strong evidence that dots are moving rightwards. Each of these arrows here reflects evidence accumulation on a single trial. So most of the time, the participant does correctly say if this boundary is moving rightwards, or this is a correct response. Most of the time, the participant does say that the dots are moving correctly. And so most of the arrows point towards decision A. And if we draw a histogram of where these decisions fall, we end up with something that looks, a lot like this canonical RT distribution, right? But because evidence accumulation is a little bit noisy, we're occasionally going to hit the other decision boundary just by chance, right? It's a stochastic process. So the weaker the average drift rate, the more likely it is that we'll hit the wrong boundary just by chance. And when that happens, you'll note that typically you'll make the wrong decision a little bit slower. And the stronger the average drift rate, the more likely it is that we'll consistently hit the right boundary, and we'll do that quickly. So just to illustrate this idea again, in a different sort of context, we can look at a trial where the evidence is very weak. In fact, all the dots are moving completely at random, and so there's no real evidence here for you to accumulate. It's all noise. In this sort of scenario, you can see about the same proportion of responses drift to each of these decision boundaries. And because the drift rate is very weak, because the evidence is very weak, the reaction time distributions are going to be fairly slow. Okay, so we can also model how much evidence is required in order to execute an action. All right, so if it's imperative for you to decide correctly, you'll want to accumulate a lot of evidence before you're ready to make a decision. We can model this as basically being a greater distance between the two decision boundaries. So that the more cautious you want to be, or the more evidence you want to accumulate before making a decision, the wider those boundaries are going to be. And we'll call that parameter the threshold. So again, we can provide a concrete example of incentivizing participants with, well, I'm in America, so this is US currency, $100 if they respond accurately. And of course, if $100 is on the line, you want to be more cautious. The time costs of responding more slowly are nothing compared to the ability to win $100. And so because of that, you want to accumulate more evidence and make sure that you get it right. So what we're going to do, as you can see in the green arrow here, is increase the value of the threshold that makes the decision boundaries further apart from each other. So what I've done here is I've left the drift rate parameter alone, right? It's the same drift rate. But we can see something interesting that comes out of that. If we keep the drift rate constant, but we increase the threshold, we expect that the resulting reaction times are actually going to be a little bit longer because you need more evidence in order to execute an action. The idea behind the third parameter, which we call bias, is pretty simple. In many decision contexts, we would not expect that people would be biased towards one response or another. And so we could safely assume that the starting point of the drift process is just halfway between these two decision boundaries. But let's say that we're making a value-based decision between two foods. One class of foods is junk foods versus more healthy foods. And one of my many vices is that I love junk foods. And so I'm personally going to be biased towards choosing the Cheetos here. Every once in a while, I might choose the kale, but I'm going to be really partial to the Cheetos. So what I'm going to do is actually move the starting point towards the Cheetos. And what that does is if I keep the drift rate constant, you'll note that this increasing the bias towards one boundary increases leads to faster reaction times. Another example of maybe clinical relevance is in neurological disorders like Parkinson's, for example, where motor responses can become sticky. A patient might press the same button just over and over and over, not necessarily because it's what they want to choose, but because it becomes habitual, basically. And in those kinds of situations, it would be important to try and model that out as a starting point bias. All right, the final parameter of interest is non-decision time here. And basically, this just captures everything that's not related to the decision-making process itself, right? So this captures maybe the time it takes for the visual and perceptual systems to process stimuli, the time it takes for the motor system to execute the button response once a decision has been reached, in the mind or whatever, and so on. In practice, I often see this just basically treated as a nuisance parameter. What I mean by that is that it counts for some of the variability in reaction times so that it doesn't bias our estimates or our interpretations of other parameters. Okay, and so non-decision time is just going to move that reaction time distribution left or right in time. Okay, so hopefully now that you know a little bit more about these parameters, you can look at this complex looking figure and understand what it means, right? So I don't have time, I think, to fully discuss these extensions to the DDM, but I can provide some examples briefly if you're interested in learning more. The idea of variability basically refers to the amount of trial-by-trial variability in these four main parameters, and that can potentially tell you something interesting about the cognitive processes involved. In practice, these parameters require a lot of data to estimate, and so they might have some interesting applications in psychiatry, but the benefits are probably outweighed by the cost of having, Parkinson's patients complete thousands of trials to be able to accurately estimate these parameters. Just might not be feasible. The other two I'll give a little bit more attention. One idea is about collapsing bounds in the DDM. And this refers to the idea that the decision bounds are not static, but as time increases, they start to collapse towards each other. You might know this as the feeling, as when you're standing in line for a restaurant and you're trying to figure out what to order from the menu. And when it's your turn, you still haven't decided, but you look behind you and there's a giant line behind you. So faced with time and social pressure, maybe you make a snap decision because you don't have the luxury of being able to accumulate more evidence. Attentional DDM is another interesting sort of extension. And it says basically that the drift rate is going to be higher for a particular choice when you've directed your attention to that choice. So this sort of model typically uses eye tracking to get a sense for what option is visually being attended to, and it will selectively increase the drift rate for that option. So in this example, you can see that while you're looking at the candy, the value signal starts to drift towards the candy option. But once you stop looking at the candy and you start looking at the chips, the value signal instead starts to drift towards the chips option, and then back again when you start looking at the candy. All right. In the remaining time, I just want to give you quickly a concrete example of how my collaborators and I were able to use DDM to investigate something that's far outside its typical use case, which is to give us some mechanistic insights into moral conformity. So just to quickly go over some of the methodology, we had participants play an economic game where player A starts out with $10, player B starts out with nothing. This player A can give any portion of that money to player B. Fairness norms, of course, dictate that about 50% of the money should be shared. But to the extent that player A acts selfishly and violates that moral norm, of course, less money is shared with player B. But then there's a twist, which is that player B gets to redistribute the money. The compensate option is like cost-free forgiveness, in which player B gets exactly as much money as player A originally kept for themselves. The punishment option is basically cost-free revenge. A gets the amount of money that they had originally offered player B, and player B gets about much money as player A was originally going to keep for themselves. And what you'll note is that in both cases, player B, in blue here, walks out with the same amount of money. The only thing that differs is whether player B is punishing player A for violating a fairness norm. That's the big takeaway here. It's a punishment game about moral norms. And we want to see how people's preference for punishment changes as a function of what other people are doing. So in the group condition here, you can see what decisions are being made by 4 other people. And you can see in this example, the majority of the group actually favors punishment. And so you might conform, seeing evidence from the group that punishment is valued, and punish yourself. Of course, we need a baseline to compare that against. And so in the alone condition, we can see what participants' decisions are like in the absence of any sort of social influence. And we can examine the decision-making process, comparing what happens when people are deciding by themselves versus deciding in a group. There's one more little fold that we were interested in, which was whether participants' conformity would change depending on whether they were a victim or a juror. When you're a victim, you're the one who's directly harmed by the moral violation. When you're a juror, you're actually a third party. This decision doesn't affect you monetarily whatsoever, but you're making a decision on behalf of somebody who is wronged, right? Okay, and so you can see here that the behavioral results are about in line with what we expected. As the percentage of the group increases that favors punishment, so does your own rate of choosing a punitive option. Interestingly, it seems that when you're a victim, you don't actually distinguish all that much between different levels of fairness violation. All of these things seem equally bad to you. Whereas when you're a juror, the more unfair the offer, the more punishing you're going to do. And it's as if you're tapering your response depending on how unfair the punishment, the offer was, or the norm violation was. And so what we wanted to test were some longstanding hypotheses in social psychology about why people conform. One hypothesis is that being part of a group makes you less vigilant about your decisions. And the other is that groups provide evidence about what is at least socially valued. The problem with our behavioral data is that it can't tell us why people are conforming to other people's, to a group's punitive preference. So this is where DBM really comes in and helps us, because these parameters are all psychologically interpretable, okay? So we've already gone through these, but I'm just going to give you a sense for what these things mean in context. So the bias term tells us how much do individuals prefer punishment in the absence of group influence. Threshold parameter tells us to what extent do groups cause individuals to relinquish moral responsibility. The drift rate parameter tells us to what extent do groups provide evidence that punishment is at least socially valued. And you can see in this diagram here, in this sort of case where the group is evenly split, that you might have some pre-existing preference for a non-punitive response. And so in addition, the drift rate just kind of slowly drifts towards the non-punitive option here, producing this sort of reaction time distribution. Just to fly through some of the results, what we find is that people are actually more cautious when the group is evenly split, which is what we see in these purple bars here, or when they're choosing by themselves, which is shown by the gray dashed line, right? Compared to when a majority of people either favor forgiveness in the blue bars or punishment in the red bars. And so because the threshold parameter is an index for sort of caution or the amount of evidence needed to make a decision, our interpretation of this is that people relinquish moral responsibility when there's a majority in the group. They decide less cautiously as a consequence. They might be thinking to themselves, well, I'm only one vote out of many. What does my vote matter? And so they choose less cautiously. The drift rate results are pretty clean here. We find that the more that the group endorses punishment, the more participants are accumulating evidence in favor of punishment. All right. And so what we take away from this is that groups provide evidence that punishment is socially valued, and this can help lead to conformity. All right. So that was just sort of a whirlwind tour of what the DBM does. So remember CREAM, choices, reaction times, enable, accuracy, speed, trade-off modeling. We talked a little bit about how this model works, and then I've given you maybe just a little flavor for how we have used this model in our own work to answer what we think are psychologically interesting questions. So I do want to point you towards some open resources and materials that you can use if you're interested in learning more about DBM. If you're going to be part of my tutorial group, we're actually going to get a chance to play with these models together using a really nice Python package that uses hierarchical Bayesian parameter estimation to estimate DVM parameters. And so if you're going to be part of my tutorial group, I'm really looking forward to that. If not, and I have somehow sparked this great interest in DVM for you, you can access some of these tutorial materials on my GitHub page. And these slides will be made available to you, so you'll have the link. So this GitHub repository will include installation instructions, some sample code, and so on. If you're interested in looking at some of the data and code from the project that I just presented and see how everything fits together, all of the materials are available on the Open Science Framework. And if you're interested in reading the paper, you can read it here. It's open access, so you should be able to access it. All right, and that's everything I've got. So perhaps we could do the Q&A now.